Hey guys, welcome back to another video. Today we're going to be deriving a formula for the Fibonacci sequence that's not recursive. Okay? So, if you don't know what the Fibonacci sequence is, the first two terms are 1. Okay? And then the next term is characterized by the sum of the previous two. Okay? So, the first two terms are 1. The next term is the sum of the previous two, so 1 plus 1 is 2. And then the next term is 1 plus 2 is 3. And then 5, 8, 13, 21, 35, on and on and on in this sort of fashion, okay? Okay, and it's characterized by the formula. The term is the sum of the previous two, like this, okay? But this formula is a recursive formula, and if you wanted to calculate something like the 100th Fibonacci number, then you have to calculate all the 99 Fibonacci numbers that come before it. That's not very efficient, and there's a better way. So the idea here is you use linear algebra, okay? So we're going to add a second equation, okay? Because there are two variables right here. And we know that this is trivially true. Okay, we put it in its vector form. F of n minus 1 is going to be equal to 1, 1, 1, 0 times f of n minus 1, f of n. Okay, cool, like that. Now we see it's still recursive, but what we can do is we can take this and apply it back into the formula, okay? Doing that, and we get 1, 1, 1, 0 times this part right here. When you plug that back into the formula, it's 1, 1, 1, 0 times f of n minus 2, f of n minus 3. Okay, let's go ahead. We can go ahead, combine these two, and we get 1, 1, 1, 1, 0 squared applied onto f of n minus 2, and I'll make this f of n minus 3. Okay? And the idea here is that you could keep on plugging this in to the formula, and you could get something of the form 1, 1, 1, 0, the kth power applied onto f of n minus k, and f of n minus 1 minus k. Okay? Alright. Now, what we'll do is we will plug in n minus 1 for k. Okay? So, we plug in n minus 1, we get 1, 1, 1, 0 to the n minus 1's power times f of n minus n minus 1, okay? And then f of n minus 1 minus n minus 1, okay? Which is going to be equal to 1, 1, 1, 0 of n minus 1 applied to f of 1, f of 0 right here. What is f of 1 and f of 0? Well, this is our 0 place, this is our 1 place, okay? Or our 0th term and our first term, okay? So this is going to be, oops, sorry about that. It's going to be our matrix applied on to f of 0, f of 1, which just turns out to be 1, 1. Okay, now, you see, we turned our recursive formula into something that is not recursive, okay? It's just a flat-out formula based on n, okay? The thing is, it has this right here. It has this 1, 1, 1, 0 to the kth term. It has this thing in the formula. And, if you try to calculate this, it's very difficult to do this. And so, we're going to go ahead and use diagonalization to make this a bit easier for ourselves. If you don't know what diagonalization is, then you should watch my previous video on the idea behind it. This video is going to be more, computation. So, let's go ahead and try and figure out 1, 1, 1, 1 to the k. So, what we want is sum x, such that a of x, okay, this is our a to the kth power right here. A of x is equal to lambda x. Okay, and if you find x and lambda, then what we can do is we can have s be two values x1 and x2. And we could have D, which is a diagonal matrix with the form lambda 1, 0, 0, lambda 2, okay? And then we have S inverse, which follows this properties right here, okay? Now, why do we need this? Well, that's because a to the k, I guess I'll write it right here, a to the k is equal to S, d to the k S inverse, and of course d to the k is some diagonal matrix, to the k, which actually turns out to be lambda 1 to the k, 0, 0, lambda 2 to the k. And I suggest you to try to prove this right here. Okay, so now that's why we want this. So let's go ahead and mess around with this formula right here. Okay, so a to the k, a applied to x is equal to lambda x. Well, notice on the left side here there's matrix vector multiplication, and on the right side here there's a scalar vector multiplication. So to fix them two types of multiplication, we're going to go ahead and turn the right side into a lambda I of x. And these two are equivalent, okay? You can go ahead and check this for yourself. Now we're going to subtract it to the other side, so we get ax minus lambda ix equals to the 0 vector, okay? And what we can do is we can factor out an x, okay? And I suggest you guys try and prove why you can factor out an x, okay? Now, one thing here is that, wait 1 second. Okay, one thing here is that if for any matrix right here, if x is a 0 vector, then it's always going to be the 0 vector, okay? So, and we don't want x to be the 0 vector, because then we'd have very boring matrices for this. And, we wouldn't have any lambdas. So what we're going to do, we're just going to say that x can't be the 0 vector. Okay? Now, if you take that means you take a non-zero vector to the 0 vector. So that means the determinant of this linear transformation, okay, of this matrix is in fact 0. Okay? Now you can go ahead, do some computation. So this determinant right here turns out to be the determinant of 1 minus lambda, 1, 1, and negative lambda. And this is going to be equal to negative lambda times 1 minus lambda. Okay, minus 1. And this is going to be negative turns to positive, lambda squared minus lambda minus 1. And this is all equal to 0. Okay? And this is our characteristic polynomial. So, that's really important. I'll go ahead. I'll write it right here. Okay. Lambda, oops, I guess I can do some better. Lambda squared minus lambda minus 1 equals 0. We won't solve for lambda just yet, but we have this polynomial that describes it. Okay, so now we go back a couple steps. So, we're going to go back to here. Okay, we're going to go ahead and have x be xy, and we're going to go ahead and create a system of equations that describes this. Okay, so our system will look like 1 minus a lambda. Hold on, let's go ahead and just expand this out then. So this matrix right here is going to be 1 minus lambda, 1, 1, negative lambda, applied to x, y, and this is going to be the 0 vector. So this has 1 minus lambda x plus y equals 0, and then x minus lambda y equals 0, okay? And now we see that this bottom equation means that x is equal to lambda y, okay? And actually, because x is not a 0 vector, and x and y are just equivalent with like a constant right here, this actually means that x can't be 0 and y can't be 0. Because if one is 0, the other is 0, and that means the vector is 0, okay? Now that we know this, we can go ahead and plug it back. So we get 1 minus lambda times x. Oops, nope. 1 minus lambda times x turns into 1 minus lambda times lambda y plus y equals 0. And now that we know that y is not 0, what we can actually do is we can divide by y, and we get that 1 minus lambda times lambda plus 1 is equal to 0, which is equal to negative lambda squared plus lambda plus 1, sorry. And since this is equal to 0, what we can also say is we could multiply by negative 1 on both sides, and we get lambda squared plus lambda plus 1 right here. Think about it, here is that we have this and we have this, okay? So that means that this is true. What does that mean? That means y can be any value as long as it's not 0, and it'll satisfy this. So what we're going to go ahead and do is we're going to set y equal to 1. That means that x is x and y. So our x is going to be our xy, so our y is 1, and our x is lambda y, so our x is lambda. Overall, our x vector is lambda, comma, 1. Okay, now we're pretty much all set. Now the thing is, we need to find a couple x vectors. How are we going to do that? We only found one. Well, the thing is, lambda actually has multiple values. If we go ahead and plug this into the quadratic formula, we see that lambda is equal to 1 plus the square root of 5 over 2, and 1 minus the square root of 5 over 2, okay? And these are actually some important constants in mathematics. This one is the golden ratio, and this one is the conjugate, so I'll just call that phi bar, okay? So we have phi and phi bar as lambda. So that means we can go ahead and write our x as a phi 1 and a phi bar 1, okay? And we know our lambda 1s and our lambda 2s. Okay, nice. Now we just go ahead and do some cool stuff. Okay, we're almost there. So we know our x is gonna be our x's. So it's gonna be our phi 1, phi bar 1. There we go. We know our d is gonna be the corresponding lambda, which is just phi 0, 0, phi bar. And we know our S inverse satisfies this property. Okay, and you can go ahead and figure out the inverse pretty much any way you want. I went ahead and just used the definition. And if you do that, you'll find that the inverse, hold on 1 minute, you'll find that the inverse, S inverse, is equal to phi bar minus phi to the negative 1 times the matrix negative 1, 1, phi, phi, oops, negative 1, 1, phi bar, negative phi, like that. Okay, so now we have our S ds, so negative 1, and we know that our a to the k is equal to S d S inverse, so let's e to the k right there, and of course we know that. Okay, so let's go ahead and plug it in. So here is what we're going to do. We know that our f of n minus 1 is equal to a to the k applied to 1, 1. So we're going to take it slow, step by step. First things first, we're gonna put in our s, d to the k, s inverse 1, 1. Okay, so our s is going to be 5, 5 bar 1, 1. Our d to the k is gonna be 5 to the k is 0, 0, 5 bar to the k because of that property we discussed earlier. Our 5 bar is gonna be, our s inverse is gonna be 5 bar minus 5. Hopefully you guys can see to the negative 1 right here. And then times negative 1, 5 bar, 1, negative 5, applied to 1, 1. Okay. This got a little bit messy, but okay. I can go ahead and erase this. Alright, so now, let's go ahead and work through it step by step. 5 bar minus 5 to the negative 1. 5, 5 bar, 1, 1. Okay, so 5 to the k, 0, 0, 5 bar to the k. Okay, multiplying these two, we get 5 bar. Let's see, multiplying these two, we go ahead and we get 5 bar minus 1, 1 minus 5. Okay, and then multiplying these two, we get, and basically we just continue. We just continue on like this, applying it to vectors and such. And if we go ahead and keep on doing this, what we get? We get that, I'll just go ahead and put the answer since I did this computation before. F of n minus 1 is equal to 5 bar minus 5 to the negative 1 times the vector 5 to the nth power 5 bar minus 1 plus 5 bar to the nth power. And the reason why I'm using 5 and not, the actual 1 plus root 5 over 2 is because I like it in this form better. Plus 5 bar to the n, 1 minus 5. And then there's something down here. That doesn't matter since we only care about the top row because we only care about f of n. Okay, from this we get that f of n, okay, our nth Fibonacci number is going to be 5 to the n, 5 bar minus 1, plus 5 bar to the n, 1 minus 5, all over 5 bar minus 5. Okay? And there you go. There is our formula for the Fibonacci numbers. Now, I highly encourage you to go ahead and check this formula. How might you check it? You might create a program that loops through the ends, and you might check it like that. Or you could check it by first checking that f of 0 is 1, and checking that f of 1 is 1. And then you check that f of n is equal to f of n minus 1 plus f of n minus 2. That's the exercise left to you guys. Okay. Hope you guys enjoyed watching. It's just been a lot of fun to make, but it's been really hard to plan out. Hopefully you guys like this linear algebra excursion. And bye guys.